Section 10.6 addresses equilibrium in a rigid body. We looked at equilibrium conditions with linear dynamics, and that was back when we were saying, we knew that Newton's second law, the sum of the forces was equal to mass times acceleration. We set an equilibrium condition to be that of constant velocity or zero velocity, so that the sum of the forces had to be equal to zero. And what that led to for us was these two expressions, that the sum of the forces in the x direction, or the sum of the x components of all forces must be zero, and that sum of the y components of the forces would be zero. Now we're considering rigid bodies, things that have dimension and shape, and so you could set all the forces equal to zero, and the center of mass of a body could stay fixed, but rotation would be a bad thing for equilibrium. We have a lot of cases where we want this object to be stationary, not rotating, not moving, and so we're going to add on a third condition when we consider rotational motion, and that is that the sum of torques must also be equal to zero. This is going to lead to a new problem-solving strategy, really an extension of the one we had before, which you should read about in the book in 10.3. A nice simple example of applying an equilibrium condition, a sum of torques equals to zero, would be the example here of a seesaw. So you have two people, one with a mass of 90 kilograms, the other with a mass of 60 kilograms, and they're sitting on opposite sides of a seesaw with a central pivot point given here. I say central, but it has a central point between the two people. Because their masses are not equal, the pivot point can't be right in between them for equilibrium. So what we're looking for here is a case where the lighter person, the 60 kilogram person, has moved farther out in order to balance about the pivot point. The way you calculate the distance that each person is going to be sitting from that central point is by using this equilibrium condition that the sum of the torques must be equal to zero. Notice the 90 kilogram person rather sitting on the left-hand side is going to create a torque leading to a counterclockwise rotation if left to itself. So that's going to be a positive torque. The 60 kilogram person, the lighter person, is going to cause a torque which wants to create motion in the clockwise direction, so that's a negative torque. So adding these two things together, if you get their magnitudes right, you can add them up to zero. And it's also a nice simple example because notice that the force, the weight, is going to be perpendicular to the moment arm. That vector from the center, well, the vector from the pivot point to the person, so that calculating a torque is quite easy. It's just the weight times that distance, in this case x, from the pivot point. For the 60 kilogram person, you have this 3 meter distance and then a weight leading straight down. In each case, the weight, of course, is going to be m times g. It's worth going into this example. It's important to go to this example 10.11 and work through this one. Like I said, this one is simple because that weight, that force is perpendicular to the moment arm for each person. So it's the first, simplest, easiest to understand example that we have. Now, having looked at the seesaw problem, we can look at a more complex problem involving equilibrium and setting the sum of torques equals to zero. In this case, this is a classic problem. You have a person standing upon a ladder, leaning against a wall, and we make an assumption. One is that the wall is frictionless. And so when you look at the point where the ladder touches the wall, the only force that can occur there is a normal force, or a force perpendicular to the surface of the wall. Looking at the point where the ladder touches the ground, there's going to be a frictional force, which is going to be parallel to the ground, and a normal force perpendicular to the ground. There's also going to be a weight of that person applied at the point where they're standing on the ladder. And finally, there's going to be a weight of the ladder itself. And for that, what we do is we make an assumption that the weight of the ladder is a force applied at the center of mass of the ladder right there. And all this becomes apparent when we draw out our free body diagram in diagram B here. Now notice In this diagram, instead of drawing just a point, as we've done in previous free body diagrams, when you're working on equilibrium conditions for rigid bodies, you need to draw the length or the shape of the actual body. We need to do that because it's going to be important to put these various forces at their correct location on that rigid body in order to calculate torques correctly. So here we see that we have an origin where the ladder touches the ground, and we've applied correctly the friction force and the normal force. We have this at the other end of the ladder, the normal force from the wall. You have the weight of the person standing on the ladder. And then here, notice we've gone to the center of the mass of the ladder, and we've applied at that point the weight of the ladder itself. So for every single one of these forces, you need to find the moment arm, or the distance from the origin. In this case, what we've chosen as a pivot point is this point B. So when calculating a torque for all these other forces, you need to use B as the origin of the vector for each individual moment arm, and then the point where the forces are applied as the other end of that vector. So for each one of these applied forces, you find the moment arm, you find that force's orientation compared to that moment arm, and calculate a torque. This is a bit of an involved example, so you need to go to page 304 and work through this. It's also helpful to go to my notes where I've worked through several other examples in detail. And of course, if you have any questions, don't hesitate to email me or set up an appointment to talk on Zoom. Figure 10.7 shows another classic problem, an actual application of physics to biomechanics. So we're going to look at what happens when a person lifts a weight in doing a bicep curl. So when we go to diagram A, we'll see the realistic depiction of a human arm with a weight here. And then what we're showing is that if C, the elbow point, becomes a fixed point of rotation, or a point about which to calculate torques, we know that for equilibrium, that weight is going to be stationary, the arm isn't moving, and you have two torques applied in this case in our simplified model. One is the weight itself producing this positive torque in the counterclockwise direction, counterbalanced by a torque generated by the bicep. So we're going to say there's this point of connection at A for the bicep, and we're going to show the tension of the bicep points off at an angle along that arm. What we do is, we've drawn this realistic depiction here, and so what we then do is come to this side, and we draw the forearm as a simple beam diagram. We set the elbow as being our pivot point, and also as a point about which we're going to calculate our torques. We draw the tension as a vector in the bicep, and we also draw the weight here. So this is simpler than the ladder example, especially since that weight is perpendicular to that moment arm. The only angle we have to worry about in this case is the angle that the tension in that bicep makes with that moment arm here in theta. But we're going to do the same thing we did in the case of a seesaw. In the case of the ladder leaned against the wall, we're going to sum the torques. We're going to set them equal to 0, and we're going to solve for the things that we might not know. In this case, we might know the point of connection of the bicep, we know the length of the arm, the weight of the mass of the person, or the mass of the weight that the person has in their hand, and we could use that to solve for the tension, as you will do in the worked example of page 305. I've also worked this example and similar ones in my notes, so it's worth going through there and reading them as well in order to prepare for the homework as well as the next exam.